Hello, fellow foodies, and welcome back. You're listening to Foodie Pharmacology, the science podcast for the food curious. I'm your host, Dr. Cassandra Quave, dialing into you today from Atlanta. And I have got a really exciting show for you today. You may have seen this research recently in the news. I saw it as well. I was like, hey, I know that scientist because she was at Emory before. And so I'm really excited to bring Dr. Louise Hecker to the show today. You could best describe her as an out of the box scientist. She's an innovator, an inventor, and really passionate, and also as an academic entrepreneur. Her work is focused on understanding the mechanisms of how normal physiologic repair responses can go wrong in aging and how this contributes to the pathogenesis of age dependent diseases. She is also working on some really exciting novel therapeutic approaches to target age dependent pathological mechanisms. Louise believes that unlocking the secrets of how the repair process becomes less efficient in aging can actually lead to new treatments that could delay the onset or even reverse age associated diseases. Dr. Hecker has a very long-standing interest in the development of new therapeutic approaches. She's led around 15 million in funding as a principal investigator, and she holds around 20 patent applications, several of which have been licensed to companies. She's also founded 5 companies of her own. Some of her most notable awards include Inventor of the Year and Inventor within the Empower Her Award, and today she works as an associate professor at Baylor College of Medicine and is also the founder and CSO at Fibronox. So, Louise, it's so great to see you here today.
Thank you so much for having me on the show, Cassie.
Yeah. So, for a bit of context for the listeners, we actually met as part of Emory's Female Founders Forum, where we got to meet with other women entrepreneurs and really get to share some cool stories. So, I'm thinking back to all those fun dinners we had together as a group, talking science and business, and I'm so excited to see your new work come out because I remember you mentioning it when it was in progress.
Yeah, thanks. That was a great program that Emory had for female entrepreneur company founders, and love being part of that program. Learned a lot, and yeah, it's great to be here now talking with you about research that back then was just more of an idea or something I had just started working on. So now we're back here and talking about the paper. So that's exciting for me.
Yeah, awesome. And for all the listeners, we're going to be talking about Louise's newly published scientific paper in the journal. The journal title is it's NPJ Aging. Is that right?
Correct. Yeah, it's a
Right.
Nature Partnering Journal, Aging.
Fantastic. I guess what's interesting to me is I know that before you did this work, you don't have like a lot of research history working on psilocybin, which, by the way, is the topic of today's episode. But you found some really interesting results in your work on psilocybin. Tell us about how did you get started in this particular area?
Yeah, good question. So yeah, I knew nothing about psilocybin really from a scientific standpoint when I started this project. This all really started because I had this when I lived in Atlanta, I lived in this sky rise, and this neighbor of mine, Aaron, we used to work out religiously 3 to 4 times a week on our rooftop, and we would just meet up there, and rain or shine, like hot or cold, we would go up there and work out. And so, over the course of years of doing this, you talk about all kinds of things when you're working out. And Aaron was constantly asking me questions about psilocybin. And he would say, well, I saw this on a podcast, or I saw this on this Netflix show. And can you tell me about this? And what about this? And, I finally said, Aaron, I'm a scientist. I can't get my information from Netflix. I have to look on PubMed. And all right, since you've asked me 100 times, I'm going to go look at PubMed and just see what's out there, what's known, and what, about psilocybin. And that's kind of how it started. And so I started reading, and immediately I was fascinated by first what was known, that there had been like 150 some clinical trials at that point, that the safety profile was excellent, that there were so many different disease indications it was being used for. And we know a lot about what it does inside the brain. But I was also very fascinated by, given all this exciting evidence and clinical data that's out there, how much we don't know about psilocybin. Like, there was so little known about what it does outside the brain. Very few published studies, relatively speaking. And I came across this one paper that kind of stopped me dead in my tracks called the psilocybin telomere hypothesis. And basically, what it was somebody's idea or opinion that this hypothesis that one person just published this idea, which was there's a lot known about psilocybin and mental health research in the clinic. And so maybe psilocybin is doing something to telomeres, which is a major hallmark of aging. And that's a mechanism by which it works across all these different disease indications. And at the time, there were zero experimental evidence to support this idea. And so I just thought, well, geez, I study aging. I can test this. And so this started this whole path.
That's amazing. I mean, that's the superpower of being a scientist, right? You come across an interesting idea or like come up with a question and you can actually test and explore that question.
Yeah. Yeah. I mean, this is why I am a scientist, really. This is the dream where, how I always envisioned it. You come up with this idea and then you go to the lab and you test it. And then, the data and everything just was more and more exciting from there on out.
That's awesome. Okay. So I guess you have this concept. You want to start looking at the impact of psilocybin on aging. How did you come up with the study design? Let's maybe start with the human cells that you worked on. How did that come together?
Yeah. So as I mentioned, I study aging in general and aging and age related diseases. That's kind of my expertise. And so one of the cellular models that we use frequently in my research is the cellular model of aging, which is a model of replicative senescence. So basically, it's just like people, cells age and poop out, and then they stop functioning and working and essentially die. And basically, it's just letting cells age naturally. And so you follow them over the course of their lifespan. And there are cellular markers to tell you when the cell and also the behavior of the cell. So like they stop dividing. They get larger. So a lot of these cellular, molecular, and morphological changes happen as the cells age. And so we just started with a model that's well validated to study cellular aging. And the experiment was simple. Let's let them age with psilocybin or without psilocybin and follow them through their lifespan.
Okay, so maybe you can paint a picture for us of what this looks like. Are we talking about like in a tea flask and you have this confluent layer of human cells with their growth media, and you're
Mhm.
able to basically look for these changes in shape and how they're behaving? And do you dose them with psilocybin every day, or is it like a one-time thing, or how did that work in the cellular model?
Yeah, sure. So cells, for the scientist people out there, cells are grown in a flask with culture media, and that media is what feeds our cells. So we come in and feed our cells a few times a week. And so the media that is normal cell food, we just supplement with psilocybin. And then what we do is we grow the cells and then they'll fill up the flask. So you have to split them and reseed them into a new flask. And as this is going throughout the cellular lifespan, we count how many times the cells are dividing. So we know how fast they're dividing. We know how many times they've divided. And essentially, at some point, they just stop dividing. They become senescent. And so that's when the cell is considered old and no longer functioning as it once was. And you can see a lot of these changes, like I said, physically, like by looking at the cells, you can tell that they have this different morphology, that they look senescent. There's a characteristic kind of phenotype to how senescent cells look versus a normal healthy cell, as well as you can take the cells and look at the cellular, the molecular level to these kind of hallmarks of aging and how those are different as the cell ages. And so that's what we did. We followed the cells and we saw that the normal cells poop out as expected, very typical as we see in this model. Whereas the psilocybin cells, they just continued to look younger, to have molecular markers that are more consistent with a younger cell than an older cell. And they did poop out eventually, but took them much longer. So it seemed like they had this kind of delayed aging. And it was dose dependent. So we give more psilocybin, we see more of an impact on cellular life extension.
Wow. So when we think about different theories of aging, I since you're an expert on aging, I thought we could explore this a bit just to kind of put psilocybin's effects into context. So many of the listeners have probably heard of like this term oxidative stress or inflammaging of this tie between inflammation and aging. Are there markers that you are monitoring in your experiment to look at those types of activities of oxidative stress or inflammation?
Yeah, so I'm actually happen to be an expert in oxidative stress. So that was the first thing I looked at. Oxidative stress, like a good analogy that I like to use is it's kind of similar to like rust. If you think of rust, right? It's you see a piece of metal getting older, you see rust forming. I mean, that's like kind of oxidative stress, of your cell is kind of like that, kind of getting rusty. And this created by oxidants which naturally accumulate with age. And so we looked at oxidative stress levels. And if you look in the paper, you can see that the age cells had oxidative stress levels that were the same or even lower than young cells at the beginning of the experiment. So that was impressive. And then we looked at some markers of oxidative stress. So we looked at NOx4, which is something that's of interest to me, a marker that is essentially the master regulator of oxidant production. And so NOx4 was lower with psilocybin treatment. So you're producing less oxidants with psilocybin treatment. But on the flip side, we looked at NRF2, which is the master regulator of antioxidant responses. And NRF2 levels were very high. So in a nutshell, what psilocybin led to was less oxidants that are being produced and more antioxidant defenses.
Wow. Okay, so you're really creating this great runway for the cells because you're reducing the damage while also improving your response to damage or enhancing resilience. Um, when I think about drivers of oxidative stress, maybe we could just break this down just to help people understand. We're talking about what's happening in a cell, but what happens in a human? Like, let's say, well, I give my students this example, the spring break situation. You're at the beach under the sun, you're smoking cigarettes, you're drinking lots of alcohol. Like, those are all things, you're inhaling pollution also from the street. These are all things that promote oxidative stress. You're eating junk food, lots of sugars. Um, how could you put it into context? Is that a good description of some of the drivers of oxidative stress? I mean, in addition to just the things we encounter as we age, are there ways that we actually accelerate our aging process?
Sure. Yeah. I mean, aging is, and I think if you really think about anything that we manifest is really a combination of age, environment, and genetics. And that's why I like studying aging actually, because it's the one thing that all of us have in common. We all have different genetics. We're all, growing up in different environments. We take in different things that, that influence that I would consider part of environment, how we eat, exercise, the sun, all of these things but at the same time, all of those factors, including age, contribute to oxidative stress. So oxidant signaling is a normal, natural part of normal, healthy cells. But it's one of those things where if you don't have enough, it's bad, and if you have too much, it's bad. So there's kind of like this optimal range where you need a certain level of oxidant signaling. But again, as we age, and all types of things can influence oxidative stress. So environment, aging itself, damage. So keeping those oxidative stress levels in check is a hard task because it's, you can hit those pathways from so many different ways, and so the fact that there is something that can slow the oxidative damage that accumulates over time is fascinating.
Now, it is fascinating. Okay, so now bringing us back into the lab. So you found these incredible results in these human cells. What was your next step in your kind of decision making process of how to take this research forward?
Yeah, so it's interesting because I just really looked at every marker that I had in the lab that I knew that was associated with aging, and everything that we looked at just worked. I was like, wow, these cells have molecular markers that look more like young cells. And so when we were able to see that data, that's really encouraging in terms of, hey, let's move this forward into animal studies. Um, Now, one thing that I was very blissfully ignorant about when I embarked on this process was I just assumed, like most projects that I work on, that, okay, well, I want to study psilocybin. So I'm going to go in the lab and I'm going to order some psilocybin and I'll start experiments tomorrow, you know? I had no idea what I was getting into because, you need a DEA license, you need a lot of regulatory controls to even have that substance in your possession. So it probably took about a year and a half from idea conception to starting an experiment. So it was a really challenging, even like if cells, anything that touches the cells, so if the media, the food for the cells touches the cells and then we take it off, we have to send that to a company to destroy it. So there are so many
Wow.
different things that you have to have in place, and you have to have DEA inspections. And so that said, it was easier to do this with cells. Once we got to animals, then we had to say to the IACUC, which is kind of the governing body that oversees our animal studies, it was really hard for me to get them to approve this study because at that time there was no research ever on psilocybin aging. There were very few, if any, long-term studies where you're going to give psilocybin high dose. So it was really challenging to even be able to initiate these animal studies, but we were able to do it. And what we really wanted to do, to set out to do when we did the mouse studies, was to come up with the most clinically relevant testing protocol. Because if you think about it, no one wants an intervention. If I publish a paper and say, well, you've got to start taking psilocybin psychedelic dose from age 5 on, nobody's going to want to do that. That makes no sense. But if you're 60, 65 years old, that's that you as you get older, I know for myself, as we get older, we start thinking about aging more and anti-aging
Yeah.
intervention. So we wanted to design something that was clinically relevant and realistic. And so that's why we started with aged mice, which or 19 months, which in the human equivalent of like 60 to 65 years old. And in the mice, we gave it once a month for 10 months. And our main endpoint was survival. And so what we found was that in the control mouse group, because mice only live, their maximal lifespan is somewhere around 30 months. So at 28 months, the 50% of the control group had not survived, whereas we had 80% survival in the psilocybin treated mice. So we have this absolutely striking
Wow.
impact on survival.
Wow. And so, here, for those of you watching the video version, we also have some images here. Can you tell us a bit about the images of the mice? What are we looking for here in terms of their fitness?
So on the left side, you have a vehicle treated mice. And as you can see, they look older. On the left, on the far left, you see the mice at the start of the experiment, and you can see they're already starting to bald, and you see some patches. And then as they get to 28 months, you see that some of these things like the hair loss is exaggerated, has gotten worse. Even just kind of the scruffiness of the fur. You see the one mouse kind of has a belly, and then the psilocybin treated mace. I mean, one of the things that was so striking and surprising when we were actually conducting this study is that we see these mice on a daily basis, essentially, and it was really clear early on in the study that the psilocybin treated mice just looked better than the other group. I mean, and so some of the things that I didn't quantify, but I show some visual representations here, is that the psilocybin treated mice, like patches of hair that were gone, grew back, or patches of hair. If you look at the bottom mouse on the psilocybin at 18 months, you see that there's some white hairs there where the arrow is. And then, 10 months later, the white hairs are gone. So the white hair grew back black. So not only are we seeing hair growth, but hair, whitening of hair turn normal color again. I mean, I wish I could find, I would like that treatment. And, just in general, and it's hard to quantify this scientifically, but just the mice looked healthier. Mice looked better,
Yeah.
less
Was
scruffy.
there behavior? I guess maybe you didn't go into depth in behavioral testing, but I'm curious, like, were there any kind of qualitative factors you all noticed with their behavior, like, or with their mobility? Were they better of mind and body? I don't know how you would test that,
Yeah.
but
I don't want to give away too much because we have collected more data than this
okay.
initial publication. But what I can tell you, and so I can't talk about the unpublished data just yet, but what I can tell you is that there are behavioral changes that were impacted in a positive way. And we have done a lot more with kind of an omics approach that you will hear from us soon on as we put that data together for publication. That is very exciting. So there are a lot of cool changes that I can't talk about just yet.
Okay. I don't want you to scoop your own
Pipeline.
stuff there. It's good. Well, that's exciting. So you're also applying kind of advanced like mass spectrometry tools to look at different signals. Okay.
Yeah,
Very cool.
yeah.
Well, I want to talk a bit about the treatment regimen. So you mentioned that they were dosed monthly. Was that right? This is not something you were giving to a mouse. They weren't having psychedelics every day. What was? How did you come up with the dosing and kind of the frequency of dosing and the actual amount of psilocybin you delivered per dose? Because as we know in pharmacology, there's just so many different factors to consider when you're running studies.
Yeah, so this was one of the toughest things that we had to figure out in terms of, how to make this a realistic study. And there were a lot of factors that went into it. So in part, we do know a lot about what's being used clinically in patients. And so since we had kind of one shot, because, we had a pilot fund, so we didn't have unlimited amount of money to do this work. We thought, let's use a higher dose, because at least if we can see an impact, we can always go back on the dose.
Yeah, that's pretty common, by the way, too, just for the audience. Like you may start higher with whatever kind of dosing. If you're looking even at antimicrobials, you're looking for that. Does this have an effect? Because also you don't necessarily have delivery optimized yet, right?
Right.
Kind of seeing will it get to the target or not? Okay.
Right. And so the other thing so we tried to model it in some way. Part of this decision about the actual dose use was about trying to model clinical trials, what we know patients have been given high dose wise. Now I've noticed like a lot of people since the paper came out have been really questioning the dosing, and some people have said, well, if this were translated directly to humans, this would be like 4 or 5 times the dose of the highest clinical trials with humans. Technically, on paper, that's true. But what that doesn't take into consideration is that, mouse metabolism and human metabolism are very different. So mice metabolize psilocybin like 4 times faster. And so the half-life of the drug is so much shorter in the mice. And so we had to not only take the actual dose into account, but how what we do know from prior studies is the pharmacokinetics and basically how fast and how long it stays in the mouse body versus a human body. And so we took those factors into consideration. The fact that it's going to be, removed metabolically, removed from the mice is essentially at such a
Broken down like,
broken down.
quickly
Yeah,
by their
yeah,
metabolism.
going to be broken down 4 times as fast, let's say. So we took a lot of factors into consideration. So this is why I caution against the general public trying to make direct translations from this, because there are so many factors that go into, how we come up with dosing and how you pick doses for different species, and why it's important not to take these findings literally and make direct translations.
Absolutely. And I think you brought up a really great point too. This was a pilot study to test an idea where in pilots, as we mentioned, you typically try and make sure that your parameters are such that you can capture some effect. And then you go into further studies to fine tune and really understand those effects and how they might translate over to humans down the road.
Absolutely.
Yeah.
Yeah.
Well,
Then there's a lot to be done there.
yeah. Well, this brings in another question of mine. This is an area that's gotten really, I think, popular in probably, I don't know, past decade or two. And this concept of microdosing. And so, there are probably a lot of listeners that do microdose or have engaged in that. And they're probably wondering, well, what about microdosing? I think if I'm understanding, we just don't know yet, right? We have to do those studies to see if that also leads. Would you say that's fair?
Absolutely. Yeah, I think there are I think if you look at the literature, there are probably more published studies on the high dosing, and there are more clinical trials that have used a high dose. That said, sure, the microdosing is gaining kind of this wave of kind of interest, and certainly people have asked me about that. Again, we have data on this that I can't share just yet, but it's going to be really interesting. And I think that the dose, what I can tell you is that dosing has an impact on different things. And so lower dose may do different things than higher dose. And we're trying to tease that out right now. So more to come, more needs to be done, and especially long-term studies. I think the other thing that's really needed is that, we have we have lots of interesting, like I said, mostly clinical data with psilocybin from short, clinical trials, or I think we need a lot more in terms of long-term studies that actually are at least starting with these types of studies, these preclinical studies, to really look at long-term dosing and what it does, not only the good benefits, but are there potential harms to long-term dosing?
No, it's a really good point, and I think it's something key. Not everyone reacts well to different psychedelics, and there's one of your co-authors, Dr. Ali Janzarabi, who's a clinician, palliative care physician here at Emory. He's given guest lectures in my course on medical botany on this practice of psychedelic assisted psychotherapy, um, which explores use of psilocybin in clinical trials for patients, which also is incredibly difficult apparently to run these studies because of the restrictions through government restrictions on how you get permissions to have the drugs in hand, to be able to deliver them to, it's extremely controlled and extremely difficult to do these types of research studies, whether you're doing them on mice or with human partners that are engaging in these clinical trials. Um, but I think there's a lot out there still to explore, and not every psychedelic is obviously the same. They're not all acting on the same exact pathways, and some are much riskier for certain patients than others. So all these things need to be kept in mind. But I really wanted to highlight the the work you're doing on aging because I think this is a start of something really exciting. So I guess the point here is that while there's a lot that we still don't know about psychedelics, and we're learning constantly through these new trials, especially when it comes to mental health. I think this road this path you've opened, Louise, is so exciting because this is the start of a brand new journey and understanding these other connections when it comes to aging. What's your hope? I mean, we have all sorts of listeners that tune into this show. I mean, you mentioned earlier that this first study was kind of restrictive because you're working with a small batch of pilot funds. I mean, are there ways that the public can help support your research? Or, yeah, tell us more about where you hope to go with this in the future.
We've got big plans. Somebody asked me the other day, like, this is a new area for you. Are you planning to stay in this area? And I was like, yeah, I am now a psilocybin researcher for life. I mean, the data is too exciting. I was immediately fascinated, and I am, if I wasn't excited about it then, I couldn't be more excited about it now. It's just a really new frontier in psilocybin research. No one's ever discovered that it has these potent impacts systemically, that can affect aging and so many other things. We mostly think about psilocybin and serotonin receptors in the brain and what it does in the brain, but what our research has shown is that it has potentially an unlimited number of things that it could also impact that we just have not yet studied. Aging being, this being the first to show its impacts in aging. So super excited about what's next. We already have a lot of things cooking. So I hope to have some more papers on this topic very soon, follow-up studies from this. The next big step is certainly to, and I'm grateful. I will say also, I'm grateful for Emory for funding this because I was able to get 2 rounds of pilot funding. And this was very high risk kind of research that had never been done. There was nothing on this topic. And, Emory was good enough to me to provide the critical funding to propel this forward. And so now the next step is to continue to find some bigger funding that can support these kind of larger scale studies that we have in mind. Because based on what we know, it's really opened up 100 new questions that we need to test. And so we'll need more funding to continue our work. Anyone wants to contribute funding, please contact me. Of course, I'll be applying for federal grants. I think traditionally the federal government has not been a particular fan of supporting this kind of work. It's been challenging to get, and if you look at what the government has funded in terms of psilocybin research, it's relatively low compared to other, kind of the traditional drug path. I think there's a lot of challenges with funding, especially because of the regulatory barriers that remain. I think once the Schedule 1 designation changes, which I guarantee will happen, regardless of my work, because it's already in phase 3 clinical trials. So if any of these trials are completed with positive outcomes, then it will be FDA approved for some indication in the near future, and that will inherently change its Schedule 1 designation. So I think that will help. The FDA has given this breakthrough designation status, so that is something that the FDA does to help the traditionally sluggish kind of FDA approval process. And that's a really great sign because that underscores the safety profile of psilocybin, that, enough clinical studies have been done to show that this is a relatively safe drug. There are very few adverse events reported in a number of clinical studies across various disease indications. So that's really exciting. I think for us, we're focused on, more of what's not known yet. So how do we dose properly? How do we optimize the dose so that we can translate this directly to human clinical trials to promote healthy aging? What age is the optimal age to start at? Is there an age where you start treatment and, you're beyond the point of its impacts? And is it too late to start taking it at some particular age? If you started at 80, is it going to have benefits versus you started at 60? Do you really need to take it repetitively? What if you just gave one dose? Would you see any difference in life extension? So along with the potential harms. So what are the potential negative impacts, if any? Is there a risk for things like cancer? You're taking repetitive. So we just don't know the answers to those questions yet. So a lot of studies have to be done to get at those important questions so that we can effectively translate this to clinical studies.
That's incredible. I mean, I think it's also for me, Louise is an ethnobotanist. It's so exciting to see something that has such value in indigenous systems of medicine from, if you think going to the highlands of Mexico and its history of use and healing practices. And of course, there are other psychedelics used by healers in different cultures. And just seeing how now modern, like Western science, is also exploring what indigenous scientists for a long time knew was something they could use to support their health. I guess one concern I have around funding this kind of work, and I'm sure you're closely following what's happening right now with the current um, potential cuts to the National Institutes of Health, is that the National Center for Complementary and Integrative Health is actually on the list of institutes to be eliminated, not revised, but completely eliminated. And that's really scary for me because I think about all the people that rely on natural products as a regular part of their healthcare, whether it's as a dietary supplement, like an herbal supplement you take to support health or immunity or fiber or whatever you're taking, from these botanicals, or those that are interested in understanding how other substances like cannabis and its derivatives or psilocybin or other similar types of plant and fungal natural products. Um, Without that institute, which already has a very small funding budget, there's not going to be many opportunities, unfortunately, to support research like this, because that is traditionally the major funding institution for these alternative modalities, which I don't even know why they're called alternative, because really modern medicine is an extension of traditional medicine. And you're, looking at ways to apply these natural products. I don't know if you have any thoughts on this or.
Yeah, well, I hear you. I hear you, Cassie. And I think it doesn't matter what you study right now. It's a tough time to be a scientist. It's a tough time in our country to be in the career that we're in. Let's face it.
Yeah.
I just kind of take a day by day approach. My job is really to do good science and to keep this project going in any way that I can. And I guess I just can't worry about what I can control. So, I will say that in light of, what the situation is for scientists and government funding right now, I will certainly be pursuing, outside avenues to secure funding. I know the good thing about this topic is it's a topic that's a broad
Yep.
interest to a lot of people. And so I'm hoping that will, work in my favor to secure funding somehow in some way to continue this project moving forward.
Yeah. Well, and I think you have a secret weapon that, you know, there aren't enough of us that do look at science, I think, in an entrepreneurial light. It takes a certain kind of hustler mindset to keep going and look for those resources because we really believe in the science. And I'm so excited about what you found already and can't wait to learn more about all these other data points that you've been gathering and see how this, eventually can perhaps help improve human health and longevity. So much for sharing this journey with us.
Thank you so much for having me. I mean, it's an exciting project, and I hope your listeners think it's as exciting as I do.
I 100% know they will. They're probably going to have lots of questions and comments. So for all the listeners out there, of course, you can comment on the podcast on Nature's Pharmacy, my newsletter on Substack, or you can do so also at the Teach Ethnobotany YouTube channel. You can support Dr. Hecker's work. I'm sure she's got links at her website at Baylor, where you can support in whatever way you're able her research. And yeah, thanks so much for coming on the show, Louise. This is really cool.
Thanks for having me.
Awesome. All right. You've been listening to Foodie Pharmacology, the science podcast for the food curious. We are excited to now be in season 7. We had a little brief hiatus this summer, but we are back this fall with lots of great episodes coming to you. If you'd like to help support the podcast, again, this is a 3-person team. It's myself and producers Rob and Christine. It takes a lot of people to make this work. And so if you'd like to support us, you can do it by buying me a cup of coffee. You can head over there. We've got the link on our website, or you've got a QR code here on your screen on the YouTube channel. Each cup of coffee gets me a bit more caffeinated, but also helps us to pay the bills to keep the show coming. So thanks so much for listening. Stay healthy out there, and I'll see you next time.